So we're going to talk in this section about motion. This is the beginning of the study of motion. Mechanical engineers study motion. Things that are moving are static. That's what civil engineers work in. We're going to look at things that are moving to start the year. Things that are moving are more interesting. Think about it, right? Would you want to stare at a blank TV screen or a TV screen that's frozen? Is that interesting to you? No, the motion that's involved, the actual transient nature of the people speaking is what is interesting to you, right? In a film or something, in anything in general. So we're talking about motion first. So we're going to talk about displacement, velocity, and then we're going to look at the graphs relating them. We're going to calculate displacement as a function of certain velocities and times. We're going to talk about some vocabulary, frame of reference, displacement, time, velocity, and then we're going to look at those graphs that we talked about. So let's start with the first slide here. This is huge. How many of you before have ever thought, and this is what I thought when I was a kid, and whatever, I thought this was true, but it clearly wasn't true. I used to ride in the car with my parents, and I have a couple brothers, and we're all into sports. So we'd always bring like a tennis ball in the car, just to like throw it back and forth, even though it was closed. It just kept us occupied, you know? And remind you, there were no such thing as phones back then, like cell phones. So we always had to find something to do, and it was usually a road game or something, but whatever it was. I remember though, and this is no joke, I remember thinking about this as a kid, and I didn't understand it then, but I do understand it now. How come when you toss the ball up and down, it didn't go up and like smack you in the face? Because logically speaking, aren't you moving forward in the car? Right? When you're in a car, the car is moving forward at 60 miles an hour, so therefore you're moving at 60 miles an hour in the car. So how come when I toss this up, it doesn't just go like that, smack you right in the forehead? Because if you've seen Bugs Bunny or any of those cartoons, the acting cartoons, they actually portray physics terribly. You'll see the road runner running, and then he runs off the cliff, or the coyote, Wile E. Coyote. He runs off a cliff, stops, realizes he's off the cliff, and then he starts to fall. Like, there would be no time for him to stop and think about it, right? The physics in those cartoons is not proper at all, or not true. And one of those things is the idea of, you throw something up and you're moving forward, it would smack you in the head. How come it's not happening? What's happening there? Comment or answer?
I had like a comment question. Like, if you were like throwing the, say, like the marker up and you accelerated really quickly in the car, would it smack you?
Okay, so that's a really great question. He's starting.
When you go in a like accelerate really quickly in the car, you just go back like that.
Yes, just me, Marco. You're way ahead. You're doing the next chapter. That's awesome. He's thinking ahead about acceleration. On the train is what happens, right?
Yeah.
How many of you on the subway hate that? When the conductor suddenly nails on the brake, right? What happens? You fall forward. It's inertia that's happening there. So in a car, because you're usually moving at a constant velocity, the marker, when tossed up, is still moving forward at the same velocity. But if hypothetically the object could levitate for long enough and you hit the gas at the same time, it would smack you in the forehead. Yep, it would. But you could try that kind of thing. And I've done it before. Like, I'm driving a road trip with my girlfriend. She'll go and take a sip of the water, and what do I do sometimes? I say, that was weird. She's like, and I'm like, oh, sorry, there was something in the road. And then she laughs. But like, it's just a mess with it, But that's physically what's happening. That's exactly it. So, whatever. She gets anything. So frame of reference. Frame of reference is about where you are physically in space and time. So if you're on a train, I'm going to give this example because it's a good example to go through. If you're actually on a train and you are traveling forward on the train, the people on the platform see you moving past, right? They believe it's an express train and they're waiting at like 68 and they see the 4 or 5 going past. They see you go past. But if you're walking forward on a train that is also going forward, what's your velocity actually? How would you describe your velocity? Not numbers, obviously. But how would you describe your velocity if you're going forward and the train itself is going forward? How would you describe it?
You would be going faster than the train.
Exactly. It would be really the sum of the velocity of you and the train. If the train is going at 30 miles an hour, and you happen to be like, I don't know, you're sprinting down the train, so somebody's freaking you out, you gotta get away, right? You're running at 5 miles an hour, which isn't that fast actually. You're running at 5 miles an hour. Compared to what people on the side look, they're going to think you're moving at 35 miles an hour. Because the train is going at 30 and you're going at 5. So it depends on the stationary or moving platform that you may or may not be on. So when you think even like bigger picture, you're on the earth right now, right? And compared to the floor, you're not moving. Agreed? Compared to people outside right now, you are the ground outside of that building, you're not moving. But compared to the sun, you're moving. The earth itself is rotating at a very high velocity. It's then revolving around the sun at a high velocity. And while that's happening, the universe itself is expanding. So in reality, you're never actually still. It's just relative motion that you're always describing. So frame of reference has to do with what your frame of reference being at that moment is. So are you on a moving platform? Are you on a stationary platform? This caused a lot of issues with the concept of Einstein's theory that you couldn't reach the speed of light. People argue that, oh, you know what? What if we could just get on a spaceship that's close to the speed of light, and then we start moving on that spaceship, and then, you add those two values together. It was still proven that you couldn't actually even come close to it. So it's really kind of interesting. But the concept of space and time travel, that idea of traveling beyond the speed of light is what you would have to do to go back or forward in time. But it's been proven you physically can't do that, using scientific laws. I wish we could. It would be really cool, but it's really not possible. Okay. I told a stupid thing in the other class. I'll mention it. I once thought, it's because we got 2 minutes anyway. I once thought it'd be a good idea to use logic to argue out of traffic tickets. And I've tried it before. One time I got a traffic ticket for parking too close to a meter. So I stood next to the meter, put my arms out, took a picture with self-timer on my phone, sent it in, said there's no way I was 15 feet or closer. My body was 3 of my body widths, and my body width is about 5.5 feet. So I knew I was about 16.5 feet away. They replied saying, well, sir, you could have moved your car and then taken a picture. And I was like, that's pretty true. I didn't think, afterward I was like, oh crap, so anybody can move their car. So I lost that one. I think I would also lose this one, but I've always felt that I could argue running a stop sign too. Think about a stop sign. A stop sign tells you to stop, right? So a friend of mine, this is one of my closest friends I grew up with, Skid Andrew. He got a ticket when we were 16 years old, right near his house. He complained about it, to this day he complains about it, because he rolled through the sign. You know what I mean, to roll through a sign? So a stop sign is supposed to come to a complete stop. What if you slow down enough and peek out and there's no one coming? You kind of just continue rolling through it like a mile per hour. You don't have to really stop. Theoretically or technically, you can get a ticket for not actually stopping. So my argument has always been when a police officer said, sir, did you come to a complete stop? Or I didn't see you come to a complete stop there. You would then argue, saying well, sir, you're never really at a complete stop, right? Because the earth is rotating and that's going around. But the idea of frame of reference would play a role. I don't think it would work, don't try it. But in my mind, I've always been can I use that to argue that? Maybe, I'm not sure. All right, we got about a minute. Let's finish with this. Let's finish with this definition here. So, the word displacement, let's write down first the variable we're going to use is x here. X or y. X being horizontal displacement, y being vertical displacement. That's the variable we're going to use. Displacement is the change in your position. This is different from distance. Let me give the example so you understand it for the weekend, so you have this thought process. If I walk to the garbage can, and then I walk back, my initial position was right here. My final position is right here. So technically, mathematically, my displacement is 0. The distance I traveled, though, will be about 6 feet plus 6 feet, so about 12 feet in distance. While my displacement would be 0 because I didn't technically change position. So when you're measuring, when you think about you're traveling from somewhere to another place, you're always measuring distance because you take a weird path. The displacement would be from beginning to end, a straight line. So we're gonna really differentiate here between displacement and distance. Displacement is straight across from one point to the other, whereas distance is actually the path you took. So say you drove from one state to another, and the path you took was the red line. That would be the distance traveled along that path, while your displacement would be the distance from A to B, the direct or straight line distance. I'm going to pause there because the bell is going to 138. So listen carefully. This weekend, you got to finish up those labs I think for you guys to do Monday. I would recommend getting a head start on stuff. You can start the problem set for section 1.3. If you didn't have the textbook, I will put up the scans for section 1.3 for the homework. You don't have to do this homework yet. Besides that, have a good weekend, guys. So we were talking about displacement, remember? And I was arbitrarily walking back and forth in front of the room. I kept saying something well, if I move from here to there and then back, it's like I really didn't move because I started and ended in the same spot. And that's the idea of displacement. So if you think about a race car track or a derby with horses, they're going to run around the track at the starting line and then they're going to finish at the starting line. So you start and finish at the exact same point. So any sort of circular race, your displacement is always actually 0 because you start and end in the same spot. I gave the example in class, if you recall, right here, where the displacement is from A straight to B. It's what we call the straight line distance. But the distance traveled itself is along this curved path the whole way. Okay, so that's distance versus displacement. Significant enough difference here that we want to understand the two. And then we'll take a look at an example to actually take a look further at that, I guess. Imagine, so in Florida, timing right now, people probably, everybody in Florida. By the way, it's funny the way things work. Last night I got this email from JetBlue. Get one-way fares or round-trip fares as low as $59. Out of curiosity, I clicked to see where the cities. Everything is to Florida and back. Because right now, everything was like demolished in Florida. So I'm assuming those flights are empty. But they sent that out with the idea of like, who would maybe want to go. But I don't really want to go to Florida right now. It's probably not the right time for it, right? I was just thinking about that last night. I'm like, really? So somebody leaves Florida, a space shuttle, they take off, they circle the Earth a couple times, doesn't matter how many times, and they land in California. Then, while this is happening, the shuttle's up in the air, up in orbit. At the same time, a photographer flies, maybe a different time, but around the same time, he flies to land in California directly from Florida to California so that he can take pictures of the astronauts as they're landing. Okay? And the question is, who undergoes the larger displacement of the two? So this is just to really emphasize the difference between displacement and distance. So here's the Earth. How would I visualize the astronauts? So make believe, I'm a terrible artist, so this is the US right here. Okay? And here's Florida, and here's California. For the sake of a better, I can't really draw well. So how would I illustrate or visualize the space shuttle? How would I illustrate that or visualize that if I were like thinking in my head? I'm going to draw what you should probably be thinking, right? So they lift off from Florida, then what do? Show me physically what would happen. Yeah, they would loop around the Earth a couple times, right? So maybe do something like this. And then they land. Okay, that's the path that the shuttle would take. Because it says that they orbit the Earth several times and circling and whatnot. Now, the photographer, while this is happening, or maybe like very toward the end of their trip, he takes off or she takes off from Florida and goes directly to California. There's that little red line right there. So the Earth is in green, the black lines are the path of the shuttle, and then the red line is the path of the actual flight that the photographer takes. Who undergoes the larger displacement here? Chris.
So they both undergo the same amount of displacement?
Good. They both undergo the same. Can you give some rationale?
They both started from the same place and ended in the same.
Exactly. That's the whole rationale here. There's no math needed. You're not calculating anything. I'm writing it out like this, saying that the displacement of the first object equals the displacement of the second object. That's why I'm writing that there. But that's the rationale there that Chris just said. They start and end at the same spot. The path traveled doesn't matter. The path traveled doesn't matter. Okay? For distance, though, the path traveled matters. So which is a larger distance? Obviously, the space shuttle. The space shuttle goes around the Earth several times and lands in California. The photographer, he or she, only go from Florida directly to California. If you just look at the line, the red line is really short. The black line is very long. So we're seeing here that the actual distance is the line itself, the length of the curved line. Okay, the length of the curved line. Questions on this concept, displacement versus distance? So here's a follow-up question to kind of like really make you think outside the box. What statement can I make about the comparison between displacement and distance? Which will be bigger than the other most of the time? Which will be bigger than the other most of the time? Are you going to have a bigger distance or displacement on most paths that you take? And I say most for a reason. What do you think, Maria? Why would you say that? When will the distance and displacement be the same? Answer that part first, because that might help you to come up with your, because you're right, but I need some rationalization. When would the distance and displacement of an object traveled be the same? Straight line. So if you go back to the previous slide, or you think about the last thing we were saying, if I go from there to there, right, the distance traveled is the same as the displacement, because the distance is the path taken, which is indeed the displacement. So most of the time, the distance will be greater than the displacement because you might take a path like this. Remember we talked about this? You take like an odd-looking path instead. So we can say the following, and maybe jot this down. Distance is greater than or equal to displacement. It's a really interesting fact to recognize. The distance traveled, it could be greater than the displacement, or it could be equal if you travel directly there. But it's never going to be the reverse of that. Again, the distance is always going to be either bigger or equal to the displacement. And that's shown here in this diagram. If I go directly from A all the way over here to B, well, the displacement and distance are the same thing. But the minute I do this, my distance traveled is greater than the direct line displacement from A to B. So distance will be either bigger than the displacement or the same. It will never be this backwards. The distance is never going to be less than the displacement. Okay? Actually, I shouldn't say that. When would that happen? No, it's not really going to happen. But when would that happen? Really think outside the box now. When would the distance traveled be less than the displacement? You don't travel very far, or you don't travel at all, yet you change position. What is that called? Come on, science fiction people. Teleportation, that's it. Teleportation would be that, wouldn't it? If I get a teleporter right here, you press the button, and I end up over there, did I actually walk a distance? I didn't really walk, so I have no distance. But wouldn't I have displacement if I somehow started here and ended there? I would have a displacement, yet not travel any distance. That's the definition of teleportation, actually, yeah. How many, this is really fun. How many fans of Dragon Ball Z in the room? Be honest if you watched it before. I love it personally. When I was a kid, I loved Dragon Ball Z. If you've never seen it, I know when I was a kid, all like guys watched it, girls in my other classes have raised their hands too. It's a really cool show. It's about these people called Saiyans. They're like warriors that protect the galaxy. But they have all these powers and stuff. And in one part, remember Goku does the instantaneous transmission, where you go from place to place? That's what I referenced to this. And I've also referenced it with infinite velocity. So we'll talk about that a little bit later. But I'll bring another reference to Goku soon when we talk about gravity. Another one we talk about power levels. So I make a lot of Goku references. He's the main character in the show that has all these like powers, pretty much. Anyway, sidetrack. This diagram here, this diagram's emphasis is just on the fact that our displacements can both be positive and negative. Our displacements can be positive and they can be negative. So if we take a look at this here, we're seeing that if I start somewhere on the left and move to the right, we're going to call that positive displacement. No matter where I start, no matter where I end, if I just move to the right, it's a positive displacement. But if I move to the left instead, it's always going to be a negative displacement. And now make sense of this. If I walk 5 feet this way, you could say my displacement is 5 feet positive. If I walk 5 feet backwards, the displacement is 5 feet negative, right? What would my overall displacement be? Positive 5 plus negative 5. What does that add up to? 0, which is why, what did we say yesterday or the other day? If I move from one spot to another and come back to where I started, I've got no displacement. My position hasn't really changed from beginning to end. I traveled somewhere, but if I compare the beginning to the ending, I'm at the same spot. That's why displacement being positive and negative matters. To the right is positive, to the left is negative. We're going to do the same thing with up and down. Up is positive, down is negative for displacement. But for distance traveled, the direction doesn't matter. We're going to get more into what are called vectors in chapter 3, a lot more of this concept. But the idea is that I can travel from here to here and then come back, and the distance traveled is the sum of the distances. So 5 plus 5 is 10. I traveled 10 feet in distance. While I traveled positive 5 in displacement and negative 5 in displacement, making my overall displacement 0, my distance traveled was 10. Okay, my distance traveled is 10. There and back being 5 and 5. So you can also jot down that distance, jot this down, distance traveled is always positive, no matter which way you're traveling. I'd probably write that at the very bottom here, as a little add-on. Distance traveled is always positive. All right, let's get into this next concept of what's called average velocity. Average velocity. This is something you have seen already. Look at that. The first form, by the way, it's the first formula of the year. Whenever I give formulas, I give units, they're in brackets and bolded like I was talking about, as meters over seconds, because displacement is measured in meters and time is measured in seconds. So the unit of velocity would be meters per second. But you've seen this already. Freshman year, what was your formula that related distance and time? What was the formula from freshman year math course that related? You used it on the summer packet at the very end with all those word problems. What formula did you use over and over and over again? This is the same exact formula, right? This is the exact same formula, just solve for r. How would you get r by itself? How do you get rid of t? What is t currently doing to r? Answer that question first. What is t doing to r? Give me the first half, Catherine. It's multiplying. So how would I get rid of t, Catherine? I would divide it. So dividing by t gives me the following. R equals d over t. Well, that's the same thing as this, really. Look at them. They're analogous. Analogous. They're the same idea. If I want the rate that something's traveling at, I can find the distance over the time period, assuming I'm going in a straight line distance. Well, now it's a little bit trickier. Now we use displacement instead of distance, and we're getting average velocity. This would actually give us speed, by the way. In your math class, when you learned about r being a rate, it's actually the speed of an object. So we're going to see speed and velocity as different things, which is like kind of ridiculous to think about because they sound the same. They sound like they're both measuring how fast you're going. But remember, for speed, we care about the distance traveled over the time. For velocity, it's all about the displacement over time. And we're going to see an example of how these two things differ in a minute. Okay? Think about the example earlier. If I go across the room and come back, what's my displacement? It's 0, isn't it? So that would make my average velocity 0 over whatever the time is. So that's kind of an odd thing to think about. Even if you move, you can have an average velocity of 0 if you start and end in the same spot because you have no displacement. Velocity is displacement over time. This little bar over a variable, the bar over the variable means constant or average. Okay, in this case, it's both. In this case, it's both. It's a constant velocity or the average velocity. When we get to the next chapter, which is chapter 3, this will be after the first test, we'll talk about changing in velocity, which we'll call acceleration. Okay, we'll talk about changing, which is acceleration. Questions on this? Yes?
So why is it average velocity?
Yeah, because right now we're not studying any changes in velocity. So we're saying that, you know what, if we know how far the person goes and how long it takes, maybe they went really fast and then slow and then fast, we're getting the average velocity for the whole trip. Now, if you want what's called the instantaneous velocity, that's the velocity at any given point. So you might be running, and then walking, and then jogging, and then running again, or you're in stop and go traffic. So this would be the overall average velocity for the entire trip by taking the total displacement over time. The speed and the velocity would be the same if you traveled maybe only on the FDR north the whole time. And you didn't really turn much, you know? It's got to be a straight line for those to be the same values. Let's look at an example to see this mathematically. This is the only formula you're really going to be, for new formulas I should say, that you're really going to be held responsible for this test. And it's on your formula sheet you're going to get. You have the formula sheet already on Moodle, so you're going to get that on the first test itself. So you don't have to memorize it, you have to be able to use it. Okay, the other stuff that's formulas are like sine and cosine, but that's stuff from last year. You have to know that. During a race on level ground, Jamie drives a go-kart with an average velocity of 6.02 meters per second east. What is her go-kart's displacement in meters after 2 minutes and 17 seconds have elapsed? After 2 minutes and 17 seconds have elapsed. So, for those that have started the problem set, a couple people have asked me questions about the problem set, just the formatting and stuff. So your problem set, remember, that's the part we'll do tomorrow. 1-3, the conversions, you can pretty much just go right through them mostly. But when you get to chapter 2, I like to list give-ins and stuff. So if I'm doing a problem like this, I would solve it in the appropriate way. So what are my givens? What's told to me in the problem right away? What do I know based off just simply reading what's in front of me? Give me one piece of information. One piece, come on, anything. Just look at the problem. What values are physically given? Alex, go.
The average velocity is 6.02 meters per second.
Agreed. Now, Alex, I don't know if it's positive or negative, but I read east, right? Does everybody remember their orientation of the compass? Okay, if I think about this, this is how we're going to denote everything this year. Okay, we got north, that's N, sorry. North and south are up and down, west and east are left and right. So I'm going to call it positive velocity because I'm going east. And east is to the right, and we said that to the right is positive, and to the left is negative. Okay, so if I'm running this way, I make a positive displacement because I have positive velocity. If I'm running this way, I'm running with a negative velocity, so I'm making a negative displacement. So the direction matters for these. So I can put positive 6.02. Do I know anything else? Do I know anything else? Mr. Draghi.
You know the time.
And what does that equal to?
Since it wants it in seconds, it would be 130.
I like it, Chris. Very good. So Chris recognizes right away, well, this is the time, but take a look. Is anything given in minutes earlier? Well, the velocity is in meters per second. Look at the velocity, meters per second. So this time should be in all seconds. How do we convert 2 minutes and 17 seconds into all seconds? Just simply figure out what are 2 minutes in seconds. If you don't know, you start by doing this on the side. 2 minutes times. What's my conversion factor between minutes and seconds? Quickly, come on. Minutes and seconds, what do they convert?
60 seconds.
Yeah, so I want to get rid of minutes, so I can put the 1 minute on the bottom and 60 seconds up top. Minutes cancel. This just tells me that it's 120 seconds, but then Chris said, well, we have these other 17 seconds still, so we know that this is going to be 120 plus 17, which is 137 seconds. So we've got the actual, and I shouldn't really box that in. We've got the actual time itself as 137 seconds. That's the number that we're going to use for our time. Again, 2 minutes is 120 seconds plus the 17, making a total time of 137. So I've listed my givens. What is my desired variable? Desired variable. What am I looking for? Desired, right? Desired. What are you looking for? Yeah, Catherine. Displacement. Do you remember what variable that is? X. Very good. Very easy to say D for displacement. It makes sense logically to say D, but D already stands for distance. Okay, so the logic kind of falls out the bottom there. You can't really use it both. So X is displacement. Once we get to vertical motion, we'll talk about Y. It's the same thing. If you call it X, it just means you're moving which way? Left to right. If you're moving up and down, you call it Y as displacement. That's it. It's the only difference between the two, but they're the exact same thing. They're just variables. So I'm looking for X. My formula, state the formula that you're going to use. I only know one formula, so I can list literally just the one formula for now. Since that's the only formula that I'm concerned with, and I've got all my givens, I can go about solving this now. How would I solve for the desired variable? Remember I put this on the problem set? I put give a generic solution, solve for the variable before you plug in numbers. So I don't want you to plug in yet. I know you know V, I know you know T. You can plug in right now. But I'd rather you solve for the variable we're looking for first. So we're looking for X, right? So solve for X. What does X become? What does X become, Steve?
You take out T, so you multiply T, so you have VT.
Very good.
X.
And that's just distance equals rate times time again, isn't it? Take a look back. This is like saying D equals RT. It's kind of the same formula again, yes? Yep. So here, now that we've solved for the generic solution, generic, not the answer that we're going to actually get in the end, we need to plug in for V and T. We need to plug in for V and T. So let's go ahead and do that. V is 6.02 meters per second. T is 137 seconds. What's going to happen? Look at my units, people. Look at my units. What's going to happen to seconds? What do you notice? God bless you. What do you notice happens to seconds here? Yeah. I like that. Peter just goes like this. Like, yeah, they kill each other. They cancel out. This second cancels with this second right here. They drop off. It's just like when I change dimensions, what's in the numerator cancels with the denominator. So what units am I left with? What units am I left with? Meters. And that's what displacement should be measured in. What do I get for my solution in meters? What do I get? She came down earlier, I know. It's just a heads up, so she's over. No problem. What do I get? What do I get as displacement? To the nearest, maybe 10th. To the nearest 10th, Em, go ahead. Louder. Okay, 824.7 meters, and we'll say approximately because I rounded, right? Now, could that be negative? When would this answer be negative? How about that? When would this answer be negative? Right now it's positive. I know it's positive. Why could it be negative? Could time be negative? Is that possible? Could you make negative time? So negative time can't be negative. So when could this answer be negative?
Velocity.
Yeah, if you were traveling west, then your velocity is negative, and therefore your displacement would be negative. But in this problem, we were traveling east. Okay? All right. We're doing well. So let's talk about velocity and speed and the major difference here. So a little while ago, I mentioned to you that displacement and distance are different things, right? Displacement and distance are different. So I know already that velocity is displacement over time. Well, speed is what I was mentioning a little while ago, and I kind of wrote it on the diagram, and that's distance over time. So if we think about this for a second, when you're in your car and you're driving, the readout is called a speedometer because you're actually getting the speed. If you travel, northbound on First Avenue, it's positive velocity because you're going north, but it's positive speed no matter what. If you travel southbound on First Avenue, does your speedometer start saying, oh, you're traveling with a negative speed? It doesn't, right? Obviously, the readout is always positive. So the speed itself doesn't indicate or care about the sign. It doesn't care about the sign of the actual vector or the motion of the person. So if I move forward, it's positive speed and positive velocity. But if I move backward, it's negative velocity. It's still considered positive speed, though. Speed, the direction, doesn't matter. Speed, the direction, doesn't matter. Okay, but velocity, the direction you travel, absolutely matters. Your velocity can be positive or negative, but your speed is never going to be negative. It's always going to be positive. So quickly recall, we did this, if you recall, you did this in your summer packet, and we quickly did this in the recent lab. We talked about slope. The slope of a line is the steepness, right? Steepness. In your math class, freshman year, you called that rate of change. Remember the phrase rate of change, rise over run? It's how far up you go, how far out you go. How far up you go, how far out you go. That was your steepness, or your rate of change. Well, this is a rate of change. So if we think about this for a graph, if I think about this as displacement, I'm going to put x here, and this is time. I know you're used to seeing y on the y-axis. I'm putting the letter x for displacement. These are just variables, okay? So if I have displacement in meters and time measured in seconds, and I were to give you a graph, right, and hypothetically, let's say the first graph I give you looks like this. What does that tell me about my displacement? What's happening as time goes on with my displacement? What's physically happening? Displacement gets larger. So let's call the podium the starting point for now. Okay? This is the starting point. I start at some height, say 2. Let's give this a little marker so we have numbers here. And then every second along the way. We'll say we go for 3 seconds here, okay? So what it means is the following. I'm starting 2 meters away from the podium, because that's my y-intercept, my starting value. And then every second I'm going how far? I'm going 2 meters. So every second I need to go 1, 2 in 1 second. 1, 2 in another second. So every second I need to gain 2 meters at a time. At least close to that in the beginning. It starts to be a little bit different. But the idea here is that if I look at my slope, this is something in the lab that people really struggled with. The slope in the lab, it should have been pretty much close to pi because it's circumference over diameter. And that's the whole, connection there. Here, take a look at the slope. If I look at the slope, it's the change in the vertical coordinates right here. Well, the vertical coordinate is the displacement. So I could say the slope is the change in the displacement over the change in time. That's what the slope is, right? It's how far up you go in displacement and how far long it takes you in time. Well, that's what average velocity is. We just wrote that on the previous slide a minute ago, that average velocity is the change in displacement over time. So I could say that the slope here, I can make this, in a sense, conclusion, that the slope of a position, that's another word for displacement, we'll say for now, versus time graph is the object's velocity. Okay, the slope of a position versus time displacement meaning versus time graph is the object's velocity. So because Peter said, I'm moving further and further from the origin, right? I'm continuing to increase my velocity. Because I'm doing that, I have a positive velocity as I walk away. I'm increasing my displacement. What if instead I had done this? What if I start here and I walk this way? I'm walking this way. Statements. When I'm moving this way.
No, you have a negative velocity.
Why? Negative velocity, 100%. Why?
Because you're going left.
Yeah, my displacement is negative. It'd be like starting out here. Let me draw it with green. It'd be like starting away from the origin and moving toward it. Look at the slope of that line. Is the slope of that negative? Here, I'm going to indicate what it is. That's me standing here at 6 meters away from the origin, and I'm walking toward zero displacement. This is the zero displacement marker. Because I'm losing or walking this way or losing displacement, I'm losing my positive value. It's like I'm walking in this direction with a negative velocity. Look at the slope of this line. The slope is negative. So the velocity of a diagram like that is negative. When would the velocity be zero? When would the velocity be zero? When is your velocity zero? Simple question. When is your velocity zero? When you're not what? Fill in the blank.
Moving.
You're not moving. So that's a constant displacement. It would be something like this. All right, you know what? I started 3 meters. Here I am. 3 meters away from the starting point, right? 3 meters away at the start. And am I moving? I'm still at 3 meters or whatever, 3.5. I'm still at 3.5. I'm still at 3.5. Well, my velocity is zero because I'm clearly not moving. Okay? So the slope of that line, if you recall, is also zero. A slope of any horizontal line is zero. Slope is velocity. Slope is velocity. Slope is velocity. That's the key you need to take home from this. Okay, wait till we get to the next chapter where the graphs are going to be different than this. And we have more stuff. This is the easier version for now. So you need to get this piece down that the slope being positive means positive velocity. Slope being negative is negative velocity. Slope being zero is zero velocity. A book is moved around a table. Dimensions of the table are given. If the book ends up where it started, what's the overall displacement? If the book completes the motion in 23 seconds, what's the average velocity and what's the average speed? So, quick dimensions. 175 by 2.25. Here's the object. It travels the path around the table, ends up back at the origin. It takes 23 seconds. What's the overall displacement? Go. Overall displacement. Zero. Thank you, Steve. Why is it zero, Steve?
Backwards.
Yeah, you ended up back where you started. What's the distance traveled? So we know that the displacement is zero. That's the first question. What's the distance traveled, though? How far physically did this book move? Follow the path taken. Follow the path taken. I'm only really asking you for the perimeter, right? If you follow my pointer, if it helps. Start here, go across, go down, come back over, and back to the beginning. Literally figure out the distance traveled, which is just the perimeter of the rectangle, right? What would that perimeter become here? Close 8. You're gonna get 8 here, I think, right?
What is that?
8?
Is it 8? I got 9.
I think it should be 8.
550. Oh, 4. Oh, no, yeah, you're
Yeah.
right.
See, what I did is I just added those to 4 and then top.
Yeah.
So I get a distance traveled of 8 meters. I go 2 1/4, 175, 2 1/4, 175. Remember, distance, I don't care which direction I'm going, so I need to add up all those little lengths together. If you walk through Central Park all day, your phone, what does it tell you at the end of the day? How far you walk, right? A lot of the time now, phones do that. That's measuring distance, because it takes care of the path taken. If you're walking like this around Central Park, it's going to account for all of these different motions. But if you're, walking straight across the park, it's the same answer for displacement and distance. So when you think about this, the distance traveled, you just literally measure the path. So the distance is 8. What's the average velocity in this case? What's the average velocity? By definition, here's velocity. There's the formula. So just literally plug in. What's your average velocity if you start and end in the same spot, Maria? You got a hand up there, you're going to answer. What's the displacement? What displacement did I just write a minute ago? What's x equal to here, everybody? 0. There's no displacement, really. So if you ever start and end in the same spot, technically your average velocity is just 0, which is kind of ridiculous to think about that. But the average speed is going to be your distance over time, which is going to equal 8 meters over 23 seconds. Okay, or approximately in this case 0.35 meters per second. So these are my 3 answers. This is what was asked of me. I was asked to find the displacement, the average velocity, and then the average speed. So although it didn't ask me to find the distance, take a look please. Although it didn't ask me to find distance, I needed distance to be plugged in here to get speed. So I wrote it down anyway. See what I'm saying there? And this is not the question asked of me, these 3 were there. I think we're going to run out of time, so I'm going to ask